Okay. Start recording. Hey, folks. Good afternoon. It's afternoon, right? I lose track. Good. Tuesday. I know. I'm under the impression that, like, there are some folks that take applied optimal here in this room in the morning. Does anyone take was it propulsion, aero propulsion? Fundamentals of propulsion right after that? And then me again? I salute you all. Just stick in this room. Nick, if you could check the audio as well, that would be helpful, just because I've got a new mic today. So, all right. So, we all have some fun. Okay, you don't have to tell people it's fun to do gradient descent for your homework, but you all get some experience doing gradient descent with your homework. Okay, all right. That's good, because so much of gradient descent. Oh, I see some smiles. Hopefully, they're unironic smiles about gradient descent. So, that's what the homeworks are like. Okay, that's pretty clear. So, like, so I give you problems. You'll run into issues, right? And hopefully you work through them, right? And the office hours hopefully are very helpful, and hopefully people found the homework FAQ helpful for different things. We'll continue to add to the FAQ for different assignments. Our next assignment we'll try to drop soon, which is going to be on using gradient descent on neural networks. Okay, and hopefully you've also realized that the coding examples we do in class that I'm explaining as I go through are great starting points for your assignment. They're designed to be that. Okay. So who here is completely new to machine learning before this lecture, before this course? That's a lot of you, right? We're trying to go from 0 to 60 here. 0 to this is what machine learning is. This is how we use it, right? Now we're in the neural networks part. And you go back to the, well, and I need to add links to more of the code. I understand there are a couple links I got to update. But at the end of last lecture, we did gradient descent using backpropagation on a neural network to, like, match a curve using gradient descent. And right after I got off the line, I just changed some of the parameters a little bit. And let's see if I got it. All right. Where is it? Here we go. I got this really nice, look at that. Curve matching right there. Pretty good, right, friends? So we did that, but that's just those are layers, but those are layers that have single neural networks, single neurons in every layer. But the math continues just as we did in class for multiple of these of the neurons per layer. Okay. And you probably saw that there was a little bit of a process. We got the code in place. The code was correct, if I recall. But we're like, let's play with the step size. Let's play with this to get it to work. And guess what? That's machine learning, folks, in practice. Okay? There are little parameters you got to tune. Okay? Anyone remember what they're called? Parameters that you tune? Hyperparameters, right? These are parameters that are not optimized by the optimizer gradient descent here. They're ones that we choose. And you're like, that wasn't working. That wasn't working. Oh, let's try. Oh, that one worked, right? And you learn techniques like that. A lot of this is the engineering of machine learning algorithms. That's what we're going to talk a little bit more about today, actually. So today, 7th February, oh, no, what am I doing? Words. I'm an engineer. Numbers. 2026, so 2/17. Once I started doing year, month, day, I never went back. Okay, it sorts in all of your dates and in your computer really nicely. Okay, all right. So, a couple things when it comes to the course. Hopefully, you have your homework in. Okay, at this point, I allowed people to submit late with some penalty to the grade this time. Just please get it out. But I hope that people understand that, like, these are homeworks you definitely want to start early on. Okay, I hope people have gotten that. We will be releasing a homework number 2 in not too long, and a quiz number 2 not too long. But really importantly, we've got on Tuesday of next week, so that's going to be 24th. okay? We're going to have a project workshop class, okay? There won't be any official lecture. You're going to come in here with your project group, and we're going to discuss your project options together, okay? We'll have both TAs in here. We're going to fan out and meet with each of the project groups one-on-one, talk about what might be good ways to go about your project. So that way you can actually get started, okay, with some confidence in knowing, like, you know, option number 3 that you submitted, that might be really hard, but option number 1, that's actually going to be that's quite useful. I recommend doing this, that, or the other thing, okay? That'll be on Tuesday in class. So make sure you're here with your whole group, okay? I can count. I see exactly everyone is here from the class, every single one of you. But just in case I missed 1 or 2, make sure everyone's here from your project group. Everyone should have been assigned a project group if you were not given a project group. So we're all project grouped up. If there's any questions about that, about your project groups, make sure you message the TAs about it, okay, and they'll get back to you. All right. So that's the near term. We will be doing remote lecture on Thursday. We'll be coding up more stuff, okay? And the hope is that we'll actually start coding with some PyTorch. Okay. Not Py, yeah. No, TensorFlow. Oh, gosh. I erased those last few seconds from your mind. TensorFlow, specifically called Keras. Okay. So all those neural networks that we were coding up by hand, guess what? Lots of people have to do that. So why not make a nice library that's really easy to use? Okay. So we're going to show all that cool stuff we were doing and coding up by hand using NumPy. You could also do with Keras. Okay. I'm going to show how that works. And then I'll give you an idea. It's like, oh, I can do this for my project. It'll make everything a lot easier. All right? Okay. Moving on. Drop frames. We're good, right? Fantastic. Okay. Any other questions course-wise? Okay. I also say, I'm sorry people had to keep dragging their data onto their Google Colab notebook. We're going to see if we can figure out a solution to that in the future. Okay. But we'll figure that out for their homework. All right. So, like I said, when we were doing this little neural network, trying to get that to converge, to fit one thing to the other, right? There were some decisions we had to make about step size, okay, what the data was. Also, on your homework, some people started the homework right away. Did anyone get like numbers that are getting crazy, crazy big? And yes, some people did, right? Some people got that. Some people knew immediately what to do before we remembered to tell you what to do, okay? To normalize your data, okay? There are tricks like that that are very important for machine learning generally, but also for fitting neural networks specifically. That's what we're going to cover today. So talk about 2 general categories, one of which is normalization. The other called regularization. They are not mutually exclusive, okay? And you might say, oh my goodness, they both sound like they make things kind of normal. What's the difference between these 2 words? Okay, but they mean different things, all right? You want to get these 2 terms correct in your vocabulary. Normalization is a little easier to explain. This is what you did in your homework, okay? And so, but both of these things are techniques that will help you learning, okay? Normalization is when you take numbers, data, signals that are happening in your machine learning algorithm, and you prevent them from having crazy numbers, okay? In fact, you try to make them put them in a nice range of numbers. Because while intellectually computing the gradient on a number that's at x equals 1 is mathematically the same as x to the 16th, so it's 10 to the 16th. Inside a computer, those numbers are handled differently. computer numbers are stored in computers in bits, and you only have so many bits, and there's precision errors, there's rollover errors, there are errors that happen when numbers get extremely big or extremely small. And that can create problems for your algorithm, so it's best to avoid them. And the solution to that is normalizing them. So if you had data between minus 1 million and 1 million, why not just rescale it so it's between minus 1 and 1, or 0 and 1? That's actually really nice, especially when you're doing x to the 6th like you did on your homework. And believe me, it gets worse than that in machine learning. Okay? That's what normalization is. So normalization is a statistical procedure to scale numeric values to a defined range. Okay. Question? So the question is there ever time you have to rescale it back after you've scaled it down? Yeah. Yeah. I mean, if you are trying to predict something on the scale of like 10 to the like 1 million there, 1 million there, right? Then you scale down the data before you put it into your neural network. What is your neural network trained on? Scaled data. So if I were to then take that neural network model and give it to someone else to use, and it's like, excuse me, I put in 5 million and it gave me nonsense, right? So that means that you would probably want to have something at the end that rescales it back. That way you're like, oh, no, sorry, I scaled down the data. So, but it's particularly helpful for, to be clear, training. Once the training is done, you can turn it back. Okay? So it's helpful. So it can increase the speed and reliability of training across data of different ranges. Okay? And some people will experience this firsthand. They didn't scale the data on the homework, and they were like, the training just fails. It blows up and sends me like huge number errors, right? And then the only way I was able to get it to not do that was to change the step size to be so small that the gradient didn't go crazy. That would take forever. The gradient descent with tiny, tiny little steps down to the bottom of the gradient descent curve. Won't work. So it can increase the speed and reliability of that. Okay? Okay? Also, though, see, it can reduce overfitting and improve generalization. It can. Okay. Cross data. Okay. So you and your intuitively probably have an idea for how you might normalize data. Here's a whole bunch of data that I have. Here's the smallest value. Here's the largest value. Smallest value is 0. Largest value is 1. Everything else is just scaled in between there linearly. Not crazy. Okay? That's not the only way to normalize data. So let's talk about methods. There are 2 general categories how you normalize in a neural network. So two categories for normalization in the context of neural network models. Okay. One you're already familiar with. It's called data normalization. Okay. That's where you normalize the data that goes in. Okay. Another one is called activation normalization. Okay. So imagine we have this neural network. I'm going to draw some data X going in, some layer here with some layer here. Boom, 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 boom. Sorry, I will spare you the sound effects. Okay. And it all comes into some output here. Output Y, right? There's your data that goes in. That's what you did for your homework. You scaled the data from the smallest value to the largest value. I think we actually did from 0 to the largest value because I think the smallest value was 0. Okay? Called min-max normalization. We'll write that down in a second, right? So data normalization is you normalize the data. Simple enough, right? Okay. Activation normalization normalizes what happens once what comes out of an activated neuron. Okay? Because maybe those numbers go to crazy ranges. Possible. Possible. Definitely happens. Okay? So even though your data might be well scaled, when you multiply it by a weight and it goes through an activation function, it's acted into something else, goes another activation function. Maybe all these different activations are in crazy different ranges. Maybe some are super small values, like 10 to the minus 10th. That's really tiny. And some other ones might be close to 1. So huge range mathematically in terms of the numbers that people are dealing with, okay? Especially when you're computing gradients. What if you normalize the activations on the way out, right? So those are the two. So there's the active, and so the other is the activations. So data normalization, I normalize the data. Activation normalization normalizes the activation. Okay? That makes sense? Anytime you have numbers, you don't want crazy ranges of numbers. That's simple. That's why we're starting with normalization and not regularization. Very simple. So with that, let's talk about an example of data normalization. Okay. Simplest one is min-max normalization. Okay. So if you want to take some data point X and want to normalize it to some data X prime, okay, you would compute the minimum value of X and the max value of X. And you would say that, oh, X prime, that's going to be whatever, and X is the data set, going to be, hey, whatever your range is. So it's going to be what? X minus X min over X max minus X min. So if you're at the minimum, you're at 0. If you're at the maximum, you're at 1. It's not rocket science, just machine learning. I didn't mean to insult a lot of I'm sorry. I'm sorry. You do excellent work. It's very complicated. I'm oversimplifying. I hope you understand this is for students who are just learning it. They're excellent, though. Okay. Right? That's not that complicated, right? Okay, you can also do more statistical procedures. You can do mean normalization. You can do, so there's, you can also do mean normalization, where you scale it to the mean. Also potentially your standard deviation. Similarly, something called z-score normalization. Taking statistics courses, you might have seen a z-score. Well, surprise, statistics, normalization, z-score. Okay, there's any number of techniques. Okay, which one works best beforehand? It can be hard to know, but you can find where people talk about, like in textbooks or even in their papers, that where they talk about machine learning, what kind of normalization that they like to do. It works well for their applications. Actually, let me see. I'm gonna try to pull something up here. I'm gonna try something. I apologize. See if this works. Okay. Pull up a video here on YouTube. What could go wrong with this? All right. Pull something up real quick. I'm going to pull up a video. It's a little robot video. I apologize because I love robot examples. Go. Let's see if we can. Okay. Here we go. Okay. This is a very sophisticated approach here. Let's see, let me pull this up here. There you go. All right, this is the Toyota Research Institute. They do a lot of work beyond vehicles. Okay, they do a lot of robotics work. This is Russ Tedrake. He's a very well-known roboticist who, I think until at least until very recently, was the VP of was a research VP at Toyota Research Institute. He's a professor at MIT. He actually teaches a lot of courses like me that are up on YouTube. They're updated every single semester. Okay, I highly recommend them. He teaches them in such a great and accessible way. He has a course in robot manipulation. That's things like robot hands and stuff like that. And so what the Toyota Research Institute has focused on for many years now is how do you make a robot that goes in your home to do home tasks. Very challenging problem. All kinds of things can go wrong in the home, but they've made a lot of strides in academic research working with universities. And look, they're doing things like this. How do you butter your bread? Well, is that Nutella? Thank you, Nutella. It matters. Whether it's Nutella or not matters, okay? Believe it or not. Because they have different viscosities and things like that. But what they've done, so the approach that they have been big champions of, what we call imitation learning. So they will actually, what they will do is they will have a person teleoperate. There you go. This is my friend Eric. Okay, he's a really cool guy, and he is teleoperating the robot to do a task. Okay, and it's collecting data for this task. Okay, every time when he's doing that, it's the robot is recording all of the joint angles for the robot, also all the image data that it's seeing with cameras. Okay, and that's an example. That's a data set. Okay, and they collect a bunch of these examples, and they train a really complicated neural network called diffusion model. Okay, in order to then train that model to then do the task automatically. Okay, from those examples, and they had a lot of success in getting to generalize tasks from a bunch of examples. This is actually this is right now the by far leading contender for how to get robots to do manipulation as in hand tasks in a house, right? Flipping a pancake. There are worse jobs to have, right, than making a robot flip a pancake, right? Very cool. And this is also done in coordination with academia, like directly. Columbia, a professor who is now at Stanford, who was at Columbia at the time, named Sharon Song, was a big proponent of this, made this great paper called Diffusion Policy Models. Anyway, it's very cool. We're not covering that today, to be clear. But this is so important to get this working for this company. They were putting a bunch of resources in trying to figure out how to make these models work. And so Russ here, he was the lead author on a paper which they wanted to determine all those little choices, all those hyperparameters that we're dealing with, okay, for a robot, okay? for a machine learning model, let me come back to reality. For a machine learning model, which ones matter? Does it matter how much data that you get? Yes, it does matter. But they did a really careful analysis. I think the actual first words of the paper are called a careful analysis, okay, of like basically what matters. Like, does it matter if they come up with a fancy new structure of neural net that they think is going to be really helpful for what they want to do? And it doesn't matter how much data that they get. Is more data better? Spoilers is it is. Okay? But another thing that really mattered a lot, normalization. Your choice on normalizing the data mattered a lot to these to how effective it was. And they just had to experiment to figure out which one it was. Okay? Not that there isn't a lot of theory behind it, but I just want to say, as simple as this equation looks, right? Those kinds of choices matter. All right? Pretty neat, right? Normalizing your data. Okay, that's for normalizing the data. But there's not just normalizing the data. There is normalizing the activation. An example of activation, normalization, called the batch norm. Or BN. You want to learn more about more about that study that I'm talking about. There is a recent seminar by Russ. His name is Russ Tedrake. He gave a seminar at Stanford, I think last year now, in 2025, where he gave a talk about it. Okay, and he talks about, hey, how you normalize your data matters. Catch it. It's a pretty accessible talk, even if you're not a robotics person. All right. So, batch norm. And the idea is that when you are doing gradient descent, specifically stochastic gradient descent, the difference between stochastic gradient descent and gradient descent is we are randomly selecting data to gradient descent on. Okay? We randomly select some data, not all the data. Okay? So, and that group of data we call a batch or a mini batch. So the idea is that you have some layer here where you have your activations of the neural network. Right? And that those activations you would sample from your batched data. Meaning, you send in a data point, boom, 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 it goes to the thing, then it activates, comes out. These are numbers. Those are activation numbers. Okay? And then you normalize those. You normalize those activations across the batch. Okay? Meaning you have a batch of data, send in one data. Record all of these activations. Send in another data, record the activations. You normalize. Okay? You could normalize with min-max. You could normalize with mean normalization and standard deviation. Okay? Very common. Common to normalize with mean and standard deviation. And often, you can make this its own layer, a batch norm. That comes in, and out comes your normalized activations. Okay? Question? it will be you're sending in a batch of data, which will yield a batch of activations, right? Nice thing about this, like, again, it's not rocket science, this kind of math. You're not solving, I had a phrase that people, they use that phrase. Okay, where does that come from? I mean, I'll be honest. I mean, because, well, because all science is hard in different ways, all right? What I mean to say is you don't have to solve the Navier-Stokes equation, is what I mean to say. This is not, the actual math you write down in order to just implement this stuff is not that complicated. Again, you're just normalizing. You're just computing a standard deviation and a mean and you're rescaling it, okay? Oftentimes, there are also weights and biases that can go into the batch norm itself that you can optimize, okay? All right? And the good news is a lot of this is so standard, you can just add a batch norm into Keras or TensorFlow. Like, I want a batch norm here. Thank you. Put it in. So you can normalize those activations. But same concept, whether it's on the data or in the activation, you're normalizing. Okay? Any questions about that? Yes? Does it get complicated if you stack more normalizations? Complicated in the sense that it doesn't add not necessarily, okay? Because it's not like you have to, at the end of the day, figure out what happened, what, where, when, and why. You'll notice that things just get all kinds of gnarly in the middle of a neural network, right? If you ever hear people talk about the modern AI boom, and they're like, we don't know how these things work. They'll say phrases like that, right? And that sounds extremely scary. It's like it fell out of the sky from an alien, and we're using it. It's like, we don't know how this works. Not like that. That's not what they mean, okay? If you talk to a machine learning scientist, it's like, we don't know how they work because the math just gets so silly in the middle. You have a tan H of a tan H of a thing, of a moving of this, and then there's a batch norm in the middle, and it just kind of works at the end, right? So when they say we don't know why it works, they're meaning like, it's just a jumble of numbers in the middle, and at the end, something comes out, right? Doesn't mean it's magic in any literal sense. That's what they mean. So, but the good news is that, like with gradient descent, when you have your derivatives via back propagation, whatever this magical mystery, whatever this crazy thing is, it's going to descend the gradient of the loss function, and you'll get down to the bottom, and you're like, oh, look, what this lovely thing does the thing I wanted it to do. Okay? So it's, in fact, helpful to put a batch norm in a lot of the cases because it normalizes the numbers. All right. That's normalization. Question, yes. Well, what's the output of it? Like, so you're asking, like, what, like, so you're normalizing the output of the sigmoid. So like I'm going to draw a sigmoid here that will erase as soon as I lift up my pen here. Okay? Yeah, like some number will come out, and then multiple other numbers will come out along this curve depending upon what your batch was. Took all those vertical values of it, and you normalize what those are. That's super clear by me just drawing scribbles on the board. Okay? Really clear, right? So yes, the nonlinearity will come into play when you have to compute the gradient, but we have a fancy way to do that called, what is it? Back propagation, that's right. I had forgotten, I needed a reminder. Thank you. Okay? So batch norm is the thing in the middle. We didn't cover a lot of the details here, just kind of move on and talk about regularization. Okay? Any other questions on normalization? There are many ways to normalize. They're talked about. Just a sample of them. Okay? You say there's a batch of them. Thank you. Thank you. All right. He's here all week. All right. Talk about regularization. This is a much bigger, broader idea for machine learning, okay? In essence, regularization is just a way to prevent overfitting, okay? In short, remember we talked about overfitting, so recall. Our training and loss curves. may not have called it that before, but the idea is if you have some algorithm that you are training over different iterations of gradient descent, okay? Call them epochs. Some people call them epochs. I don't know why. Iterations. If it were a genetic and population algorithm, you call them generations. Whatever you call them, just know what you see. And here you would have your loss. So you might start, so for your training set, if your algorithm is good hyperparameters, we'll do something like that, right? That's your training loss. Right? Because you don't train on all the data typically, right? The thing we want to know, how do we come up with a good generalization or test loss? Because once we get here and it starts going back up, we are overfitting. Overfitting good? No, no. Don't want to overfit. Okay? We want to be right here. Okay? Regularization is all about avoiding this. Any technique that is explicitly about, or that is about avoiding the overfitting there, and not necessarily about the training data, that's regularization. Any technique that you do to help you out there is regularization. Okay? So regularization and this is how the book colloquially defines it. There's a whole chapter on regularization. Okay? The book colloquially says regularization methods are strategies to reduce test error, but not necessarily training error. Okay? There are lots of things that will help you minimize both of these things. Pick a good gradient descent step, you'll probably be good on both of them. Okay? It'll probably help both of them, I will say. Like if you, or I should say, if you have a really bad gradient descent step, these both will be terrible. Right? But picking a good gradient descent step isn't a regularization method because it'll help you train. Ooh, what did I just do? It'll help you train, and it'll also probably help the test. Right? Regularization might hurt the test set. Doesn't need to, but it might. Okay? Okay? So there are two general categories of methods of regularization. These techniques are all over the map. They're not just one thing like normalization kind of is sort of one category of things. So there is explicit regularization, and implicit regularization. Okay. Okay. Explicit regularization are methods that allow you to just take what you've got right now in front of you for your training and make a change, and hopefully it works. Okay? Whereas implicit, you actually have to look at the test set, see if it helps you. Okay? Here's an example. If I want to improve my health, okay, I could just, eat less red meats, diet, etc., exercise. These are things I can do right now that I don't need to then get my health monitored by a doctor 10 years from now to know if it works, right? Okay. However, something 10 years from now, my doctor might just prescribe Lipitor for heart disease or something like that. That's something that requires me to go check my health, check my cholesterol levels. My doctor says do this. Okay. The first one, where it's like something I can do right now, but I have to check and see if it works, is explicit. Okay. Something where I need to check later to see how the whole thing went and see what happened. Okay. So an example of explicit, or I should say explicit regularization, does not require evaluating the test set. Implicit regularization does require evaluating the test set. Okay. Does not. Let's do an example of explicit. Very common one, called parameter regularization. Particularly what we would call the L2 parameter regularization. Okay. All it means are parameters, such as weights and biases. You don't want them to go crazy. We don't want them to go crazy big. That's probably bad. It would be nice sometimes if they're sort of in a general similar range. Might sound like we're talking about normalization, but slightly different here. Okay? So, but the idea is that you add to the cost. Right now we have a cost function, or sorry, a loss function or a cost function. Could be something like a mean squared error or a categorization error or something. So an example, so sometimes we'll call this weight decay. Okay. We actually had this term in our derivation of what was it? Back prop and forward prop. Okay. So the idea is you add a cost or a loss to large values of weights. Okay. You can do biases. Weights are more important. Okay. And this L2 right there, talking about a 2 norm. Remember the 2 norm? That's the distance formula. So if you have a whole bunch of weights, square them, add them, take a square root. Ignore the square root if you want. Prefer the square root, though. So the idea is that you have your cost, J, and it has maybe all your weights in there. Okay? Call this J prime. Plus, is equal to JW, whatever your loss was before, plus call some lambda value of W transpose, W transpose W. This here, that's just doing, in effect, W1 squared plus W2 squared plus dot, 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 dot. This here is a positive constant. Okay? What this means is that if you want to minimize, so this constant, who chooses it? We do. The bigger it is, the more it's trying to regularize. But you'll notice it's directly, it could be in conflict with your actual cost. Could be a mean squared error, it could be a categorization error or something. You're kind of sacrificing a little bit of this cost for the sake of this. What is this doing in practice? It's saying, I want to minimize W1 squared plus W2 squared plus whatever times whatever this value is. You can make it more complicated if you want. It's trying to bring these numbers closer to 0. Okay? There's a lot of math behind why this can be helpful. But intuitively, it's saying that, hey, having a really huge value of W, weighting something super heavily, that's really placing a very heavy assumption that this one thing is super important. Maybe all this stuff is important. Okay? So it tends to make big things come down and maybe just brings really small things up to a similar level. Okay? What it tends to do. Some people have analogized this to Occam's razor. Who's here heard of Occam's razor? I want to give me, find Occam's razor for me, anybody? Yeah. That's really well said, Sam. So Sam said that the idea is that making more strong assumptions when you don't need them is probably a bad idea. There's the movie Contact, which made it really, really simple, and it said the simplest explanations tend to be the right ones. Okay, and that's the simplest way to put that phrase. It's not quite correct. It's about making too many assumptions, really strong assumptions. So in that movie, it's in the context of whether or not these aliens had beamed a signal to Earth. Anyway, I like Contact. It's a Robert Zemeckis film. It's pretty good. It's me right here. Oh, sorry, heart's here. Heart's here. But the idea, as analogized here to regularization, is that if you are putting super strong assumptions on certain things being very important, that might just be wrong. Let's sort of hedge our bets a little. Okay, that's my very hand-wavy explanation as to why this explicit idea tends to work. There's a lot more math behind it, though. So why is it explicit? It's because you only need to add this term to the cost function when you're training. You don't need to check the test set to see how well it did in order to implement it, right? A little term like that. Okay. It also can be just generally helpful for optimization. Sometimes in optimization, when you have a term that just does nothing, it's not in the cost, okay, then the gradient descent will be like, I don't know where to put this. There? There? Anywhere? Mathematically, it can get confused sometimes. But if you say, you know what, if you got nowhere to go, go to 0, it tends to be better well behaved. It makes the optimization curve look more like a bowl instead of having big flat region. That's another reason. So if you're doing like gradient descent, keep in mind you'll have some cost, J of W, and you'll have all your W's, your W1s, your W2s. Okay? The more your optimization looks like a nice bowl, I'm drawing a bowl. You all believe me, right? Yeah, it's a three-dimensional bowl. Okay. You look extremely convinced. Thank you. Yes. The more it looks like a bowl, the more gradient descent is going to want to go to the bottom, right? So when you're adding all these squared terms, guess what you're adding? You're adding a paraboloid, the bowl. That's L2 parameter regularization. Question. It is exactly like a ridge regression. It is exactly like a ridge regression. Okay? So you all did least squares regression for your homework. And the grad students did it with the linear algebra approach, right? If you add to that cost function, this term, it's what we call a ridge regression, RIDG. The only difference, though, is that this cost does not necessarily need to be fitting cost. And also super nonlinear in difference. Okay. Like a la ridge regression. Other questions? So there are other techniques like this. The book lists a few of them. Okay, but this is an extremely common one. You also don't need to do a 2 norm. You could do a 1 norm. 2 norm I find is cleanest. Nice little smooth paraboloid going on. Okay. That's an explicit term, explicit one. Okay. Next, we'll talk about an implicit example of an implicit. An implicit regularization called, ready for this super fancy term? Early stopping. Guess what it does? It stops early. Sometimes we're good at naming things in engineering, computer science. Okay? Keep in mind, when you go up to this curve here, if you have a test set, you don't need to check the test set when you're doing the optimization, right? We're just doing it with the training set by definition. Nothing's stopping you from checking out what your loss is on the test set, though. Hey, why don't you just check it every time? And if it stops going, and if it starts going up, stop. I know, mind blown, right? Right? Stop early, if one might say. Okay. Now, that said, I drew this really nice little curve when in fact it might go a little that, right? You wouldn't want to literally make it whenever it goes up, stop. Probably a bad idea. But what you can do is, this is your first iteration, boom, you try that one, and you store all the weights and biases that gave you that value. Okay? Then you check this one. If this one is better, forget that one and use that one. Store all those weights and biases. Continue on. And maybe if you get to a point where after 5 epochs or training iterations in a row, it doesn't improve, take your best one, call it a day. Look at this rocket science we're doing, right? Very simple. And it achieves exactly what we want. We want to hit the minimum of this curve. Let's write that out. Write that out here. So, early stopping terminates training early when it is determined that the test error is no longer improving. Okay? And you can imagine how simple or complicated you can make this. You could stop as soon as it goes up. Maybe that's a little bit too extreme, but maybe it works. Or if your problem is such that it's going up and down a lot, you might, I'm going to wait 10. See if it's better over 10 epochs, right? There are all kinds of choices you can make. One might call them hyperparameters. Okay? But again, these are tricks that aren't written as some amazingly fascinating mathematical formula, would make a lot of sense. Not that there isn't theory behind them. There absolutely is. Okay? So, and that will be increasingly helpful for upcoming neural network assignments that we'll be working on and examples. Because the examples that I gave you so far are quite simple. I was pretty careful, let's see if I can get this to work here, by looking at the range of that data, I didn't go too far outside of 0 and 1 on the x-axis, and so it's nothing too crazy, right? But if I did, I definitely need to be normalizing. It's generally a good idea, right? And when we get to image classification neural networks, that's going to be fun. Okay, you have lots of pixel values going to be multiplied by other pixel values and convolutions. You're going to be happy you have these tricks at your fingertips. We're actually at the end of where I wanted to get to today. I don't need to hold you captive the entire time. I will take a few questions. Any questions so far? Yes. Oh. Oh. I forgot. Nick, do you have the link, or do you need the link? You need the link? Okay. We'll put it up on the website so you can get it. So all I did was change a couple of the gradient descent. Worked fine. Sorry. This is the stuff that makes me happy. Look at that. Anyway, yes. Yeah? You could do anything like that. So like what you're describing is sort of like a moving average. So you're talking about early stopping and seeing if, hey, because one thing that you might see if you see a noisy, where is it? Where's my curve? Where'd be my curve? There it is. Okay, thank you. If you see a noisy curve, what do you do with noise? You filter it. What? Right? You can do that. Sure. There's probably many papers written on things like that, right? So when I say there's lots of opportunities for you to try things, there absolutely are. Okay? All right, happy to take some questions right after. We'll call it here. Have a good day.